Hi there, my name is Kizito. One of my favorite mathematical concepts is the idea of a convergent sequence of real numbers. This is the idea that an infinite sequence of numbers can get as close as we like to some unique real number, without necessarily reaching that unique real number. Here, what I mean by close can be made mathematically precise. So, in this video, I'd like to introduce you to convergent sequences by taking you on a little journey, a bug's journey, into the infinite. We'll ask and answer 3 questions related to the following scenario. A little bug sees a leafy green plant in the distance and begins crawling towards it. To get to the plant, it must first travel half the distance to the plant. Then half of the remaining distance, which is a quarter. Then half of the remaining distance, which is an eighth, and so on. There's nothing special about traveling in a direction towards the right, though. Our bug could be traveling to the left instead, covering half the distance, then a quarter of the distance, and then an eighth, just as before. So, without loss of generality, let's focus on traveling to the right and think about what we've just described. We have a sequence of smaller and smaller distances that the bug must travel to reach the juicy plant. In fact, infinitely many of these shrinking distances must be traveled by our bug. This begs our first question. How can an infinite number of distances add up to the finite distance our bug has to travel? We know such infinite sums of distances are possible because bugs crawl towards plants every day. That's not a surprise. But what are the conditions under which an infinite sum of numbers is finite? No doubt many of you will recognize our bug scenario as a famous 2,000-year-old paradox posed by the Greek philosopher Zeno of Elea. Well, the bug's journey we just described is an example of what is called a convergent sequence of real numbers. I can illustrate the idea of a convergent sequence as follows. Take a sequence of real numbers and plot as many of the terms of the sequence as you can. This produces a plot that will look like this one, where each number in the sequence is represented by a unique point in the plot. For example, if the 5th number in the sequence has a value 8, it'll be represented by a point located at position 5, 8. We say that the sequence converges to some number L if the sequence eventually gets as close to L as we like. That is, choose a tiny interval around the value L and let the Greek letter epsilon, that's the E-looking symbol over there, represent the width of this interval. Then, no matter how small we make this interval, if we go far enough along the sequence, we'll always find a position capital N in the sequence such that all of the remaining numbers in the sequence lie within this tiny interval. And if we make this tiny interval even more tiny, we just have to go further along in the sequence to find a new position, capital N, beyond which all the numbers in the sequence lie within this new, tinier interval. For convergence, we don't need any terms in the sequence to have the value L. In fact, for many of the interesting sequences in mathematics, none of the terms in the sequence will actually equal the limit L. We only need that all of the remaining terms in the sequence get as close to L as we like. Let's think about this for a bit. For a convergent sequence of real numbers, we can always ensure that all but finitely many of the numbers in the sequence are as close to the limit as we'd like. But if the numbers are all getting close to L, doesn't that mean the numbers are getting close to each other as well? That is, for any tiny interval we choose, we can always find a position, capital N, by going as far along in the sequence as we need to, such that all of the remaining numbers in the sequence lie within the interval. In effect, no matter which two numbers we pick out of the remaining numbers in the sequence, the difference between the numbers is tinier than our tiny interval. Sequences of real numbers that satisfy this property are called Cauchy sequences, named after the early 19th century mathematician Augustin Louis Cauchy. Much of the early work formalizing the notions of convergent and Cauchy sequences was carried out in the early to mid 19th century by Cauchy, Bernard Bolzano, and Karl Weierstrass. Their work forms the basis of a huge branch of mathematics called analysis. One result of their work is the following criterion for convergence. Notice how a Cauchy sequence is not described in terms of a limit L, unlike the notion of convergent sequence I illustrated. This subtle difference could mean that convergent and Cauchy sequences, although they're related, are not the same. One can easily prove that a convergent sequence of real numbers is also a Cauchy sequence. For those of you that want to try it out, you'll need to know the triangle inequality. However, the converse is also true. A Cauchy sequence of real numbers must be convergent. And there must be a real number L that the sequence converges to, even if we can't fully write down what that real number is. So, for real numbers, the Cauchy sequences and convergent sequences are one and the same. Here are a couple of examples illustrating these ideas. The mathematical constant E, Euler's number, named after the 18th century mathematician Leonhard Euler, is a real number we can't completely write down, because E is a number with infinitely many digits. However, we know that E exists because it's the limit of certain sequences of real numbers that we can prove are Cauchy sequences. And we can compute the value of E to arbitrary precision from these Cauchy sequences. For example, here's an illustration of one such sequence. A monotonically decreasing sequence whose first few terms are 3, 11 over 4, 49 over 18, 87 over 32, and so on. Another example of a mathematical constant we can't write down in full is the famous number pi. But one way to prove pi exists is to show it is the limit of certain Cauchy sequences. One such Cauchy sequence that oscillates about and converges to pi over 4 is obtained from Leibnitz Formula, a formula named after the 17th century mathematician Gottfried Wilhelm Leibniz. The first few terms in the sequence are 1, 2/3, 13 over 15, 76 over 105, and so on. Of course, not all sequences are Cauchy, and so not all sequences converge. For example, take the Cauchy sequence 1, a half, a third, a quarter, and so on, and create another sequence from this sequence by adding together these numbers. So the first term would be 1, the second term 1 plus a half, the third term 1 plus a half plus a third, and so on. This infinite sum of the reciprocals of the natural numbers is called the harmonic series. This new sequence diverges very slowly rather than converges. Diverge means that no matter how big a number we choose, all of the numbers in this sequence after a certain point are larger than our chosen number. Let's look at one more example of a convergent sequence in some detail. Suppose we have a monotonically decreasing sequence of numbers. First a half, then a quarter, an eighth, and so on. Each subsequent term in the sequence is half of the preceding term. Like the previous examples of plots of sequences, we can plot these numbers on a graph that looks like this. Pictorially, each of these gray rectangles has an area equal to a term in the sequence. The largest rectangle has an area 1/2. The second largest rectangle, an area 1/4, and so on. Let's stack these rectangles like so. This visual representation gives us a nice way to calculate the sum of terms in this sequence. We can use this graph to describe our little bug crawling downwards to reach the plant. It first covers a distance 1 minus 1/2. And then it covers a further distance that is half of the last distance covered. So 1/2 times 1 minus 1/2. After which it covers a further distance that is half of the last distance covered. So 1/2 times 1/2 times 1 minus 1/2. And so on. So the total distance covered by adding up the first 3 distances in the sequence is the sum of the areas of the first 3 gray rectangles, like so. Since 1 minus 1/2 is common to these terms, we can factor out 1 minus 1/2 and rewrite this in a prettier form. This is one way to calculate the distance traveled by the bug so far. Another way to compute the distance traveled so far is to notice that the bug has only 1/8 of the total journey left to travel before it reaches the plant. So the bug must have traveled 1 minus 1/8 of the journey. And this must be equal to the sum of the areas of the rectangles. Notice that 1/8 is the same as 1 divided by 2 to the power 3. So we can rewrite this. And this is very nice, because now we have shown that the sum of terms in our sequence, on the left, must equal this nice simple formula on the right. So, by n is equals to 3, our bug has traveled a distance of 1 minus 1 divided by 2 to the power 3. And, in general, the sum of the first n distances in our sequence is 1 minus 1 divided by 2 to the power n. The bigger n becomes, the smaller 1 over 2 to the n gets. We can make 1 minus 1 over 2 to the n as close to 1 as we like. That is, we can get our bug as close to the plant as we like by choosing a sufficiently large n. And for all values of n bigger than this sufficiently large n, 1 minus 1 over 2 to the n gets even closer to 1. Essentially, we now have an argument that shows the sums of distances, first 1/2, then 3/4, then 7/8, and so on, converge to the limit 1. We now have the answer to our first question. How can infinitely many distances add up to a finite distance? Well, it's because the sums of these distances form a Cauchy sequence. If we go far enough in this sequence, the difference between any 2 of the remaining terms in the sequence is as small as we like. So there exists a limit. In this case, that limit is the total distance 1. And the sequence of the sums of these distances converges to 1. This is great. Now, on to the second of our questions in this video. Notice that this idea of halving distances as the bug gets closer and closer to the plant can be applied to any interval along the bug's journey. So, for instance, to complete the first half of the journey, the bug must first travel 1/4 of the total journey. Then 1/8 of the total journey. So 1/4 plus 1/8 is 3/8. And then the bug must travel a further 1/16 of the journey, and so on. This sequence converges to a half, but never reaches it. Or consider what happens in the second interval, after the bug has traveled half the distance of the total journey. Using similar reasoning, you can show that the sequence of distances, 5/8, 11/16, 23/32, and so on, converges to 3/4 of the journey, but without ever reaching 3/4. Indeed, in every interval along the journey, the distances the bug has to travel never ends. There doesn't seem to be a final distance that the bug has to travel in each interval. This is strange, and it implies even more strangeness. In each interval, there is no initial distance either, because we can reverse this argument, in a sense, to create sequences of distances that never reach but converge to the start of any interval along the bug's journey. Think about it some more, and you should see that this also implies there isn't a smallest distance anywhere along the bug's journey. So, if all of this is true, and it seems to be the case, how do we describe the fact that the bug actually moves? We'll see that the mathematics of convergent sequences provides a nice answer to this question as well, but only after we've introduced an extra dimension to our description of the journey, a time dimension.